Okay, so this is what we are going to do today. Some notes about exponential growth and decay. So we have some variables over here that deal with both of these formulas, which you don't really need to have the formula on the formula chart. You can just understand what growth means and what decay means, and you can create your exponential function. So y represents the final amount after some kind of growth or decay. A represents the initial, which is also your start. R represents the rate of change expressed as a decimal. So let's say I have a percent rate of change. I need to know how to change that percent to a decimal. So as a reminder, you move it 2 decimals to the left. And if there's a spot there, nothing's there, you put a 0. So 5% written as a decimal is 0.05. So always change your decimal whenever you have a percent. You would move it 2 places to the left to make it not a percent anymore. T represents time. So over time, either your amount is increasing, which is a growth, or decaying, which is a depreciation or a decrease. Exponential growth. So examples of exponential growth would be population increases and growth of monetary investments are examples of exponential growth. Another example would be simple interest. Compound interest was on here, but we do not have to focus on compound interest this year.
You're recording and I almost made a comment.
Shh, I am recording. If we look at the equation, it says y equals a 1 plus r raised to the t. So a is our start times 1 plus the rate. So because it's growing, we're going to add 1 to whatever rate it's increasing by. And then our exponent will be how much time is going by. Decay is population decreases or car or investment depreciation are examples of exponential decay. So the amount is decaying rapidly. So it's y equals a, which is your start, parentheses, 1 minus r raised to the t. So these are the same formulas, except for growth, you add 1 to the rate. Decay, you subtract from 1 for the parentheses here for what the rate is going by. So we'll do our first one, exponential growth. Population of the United States has been increasing at an average rate of 0.91%. If the population was 303,146,000 in 2008, predict the population in 2020. So let's look at what A is. A represents the initial amount or the start. So go ahead and put the original population. Then our rate, written as a percent, is 0.191%. From that, you need to write it as a decimal. So we're actually going to move it over 2 places to change it to a decimal. I know it's a decimal percent, but we don't want the percent anymore. So we're going to move it over 2 places. So in those 2 spaces, I'm going to put zeros. And then time is how much time has gone by. If we're at 2008 to 2020, yep, that's 12 years. So we're going to substitute into the equation. I want to write the equation down real quick. Y equals a, parentheses, 1 plus r raised to the t. I'll do a little cursive t. So let's plug in what we have. Our start amount, 303,146,000. 1 plus the rate raised to the 12. So this can be exchanged for any number, the 12. So if you just want to know in 2010, you'd put a 2. So you would just pay attention to how many years have gone past, and you can exchange that number with other numbers. So we're going to simplify. So whenever you add the rate plus 1, you get 1.0091 raised to the 12. So anytime you have an exponential function that has the base of the exponent above 1, that means it's a growth. It's going to be increasing. So we're going to use our calculator to plug this in. So go ahead and do that. So this is what I got. So the question asks, what was the population in 2020? We're predicting. So we're going to have to round. We're going to round to the nearest whole number. So that's going to go to 77 at the end because that 9 is going to make the 6 round up. And this is talking about population, so this is dealing with people. So we're at people at the end. So 337,957,677 people. All right, so that would be exponential growth. So let's close that and let's go to the decay one. Population decreases or car or investment depreciations are examples of exponential decay. So instead of adding 1 to the rate, we're going to subtract the rate from 1. So let's look at this first one. Nathan bought a very fancy boat for about $125,000. If the boat's value depreciates at a rate of 15% per year, what is the value of the boat at the end of 10 years? So we first need to identify our variables. So A is our start amount, 125,000. Our rate is 15%. And we have to change that to a decimal. So move the decimal over 2 places. So that's 0.15. And time is 10 years. We'll write down our formula. Y equals A, 1 minus R raised to the T. So plug in our starting amount. So 125,000 is how much the boat originally cost. And over the years, over every year, it depreciates by 15%. So we're going to subtract 1 minus 0.15 and then raise it to the t, which is how many years are going to go by. So 10. So y equals 125,000. 125,000. If I have 1 and I take away 0.15,
0.75.
close, 0.85. So anytime that your base of your exponent is smaller than 1, it's going to make your value go down. That's called a depreciation. This value determines if it's increasing or decreasing by a certain amount. Because this value is smaller than 1, it's decreasing. So plug this into the calculator. And this is money. So we need to round to the nearest penny. So that will be the hundredths place. So it'll be 30. $24,609.30. Put a dollar sign on the front of it. So imagine you bought a boat for $125,000. After 10 years, it's only worth $24,000. That's not good. So the smart thing might be to trade it in before those 10 years are up so you still have some money. All right, so what I need you to do is do these other 2 examples. So go ahead and work on that right now, quietly.
You just typed it wrong.
So I'm going to go ahead and make sure that you have the same number as me. The rate is 1.3%. So we move it over 2 places. 0.013. And then we're going from 2008 to 2020, 12 years. So it is, let me see, increasing. So it's an exponential growth. So you put the first number, and then you do 1 plus the rate raised to the 12 years. Sometimes these numbers can get really sticky, like hard to do if you don't pay attention to how many zeros there are. So that's why it's a good idea. Go ahead and put your commas in there so that you make sure you do 1, 2, 3, and then 1, 2, 3. Okay, y'all check mine with yours.
This is kind of easy.
It's good. So what is this dealing with? What should I put at the end of this?
People.
Yep, people because it's population. If you got something E to the something that's scientific notation, what I'd want you to do is just check and make sure you put the correct number of zeros in there. The last one, Olivia buys a new car for $32,000. The value of the car expected to depreciate 8% each year. So 8% is our rate, but then we move it over 2 places. 0.08. Time, it tells us 6 years. So since it's depreciating, we're going to take the rate away from 1 by subtraction. So our starting amount is $32,000. 1 minus the rate raised to the time, which is 6. So y equals 32,000. We're going to do 1 minus 0.08, which is 0.92. Think about it as 100 minus 8 is 92, and then move your decimals over. Raised to the 6. And what value is this dealing with? Or what is this value dealing with? Money. So we need to round to the nearest penny, which is the hundredths place. And put a dollar sign at the beginning. So $19,403.36. You're going to glue this in on the next page of your journal. And then we're going to look at the assignments.
This is all for real questions for the second.
Not today.
Let's get messy.
Exponential growth.
Whoa, whoa, oh no,
You like it?
like, mainly because it's.
Let's look at our assignment for today. Percent graphs. Match each graph with a scenario and a function rule. Go and write your name on it. And we are going to look at the scenarios, and that'll help us decide how to match these up. Number one, you put $600 in a bank account that earns 5% interest. So this is our simple interest. Two, you put $600 in an account that earns 3% interest. Three, you put $1,000 in a bank account that earns 5% interest. And four, you put $1,000 in a bank account that earns 3% interest. There's no numbers on this graph, but we can add them. What are the numbers going to be? And where do they come from? They come from the starting or the initial amount. What are the two initial amounts found in these four problems?
600.
600 and 1,000. So 600 would be the one on the bottom. And then 1,000 would be on top. So that should help you determine what to do next. What kind of graphs are these? Growth or decay? Growth. So put on here exponential growth. Make sure you answer the questions. And then the 6 through 9, what kind are these? Yep, exponential decay. So you have the rest of the time to work on this. If you finish this, turn it in and work on your EOC packet.